we are still dealing with the idealized basin flow that we looked at from Stommel model for western boundary intensification, but so the book calls it determination of the water surface elevation, but I titled the podcast Sea Surface Elevation just to get people interested. The ideas are the same. What are we doing? We're taking the same equations that Stommel derived flat bottom steady flow with wind forcing prescribed. So before we had done a transport by integrating those two equations of motion simplified, and we had the pressure derivative integration with surface wind stress forcing in the x and y direction and the friction at the bottom to the dependent on the transport. The idea is still that the wind forcing is able to set up the transport, and associated with them are pressure gradients which are manifest in sea surface height, right? Sea surface height is proportional to pressure gradients in these situations, and in the real world as well there are details where geostrophic flow can be derived from sea surface height gradients, but here we are dealing with a simpler situation. So we end up with another boundary value problem like before. Before we had the Dirichlet boundary condition where the gradient at the boundaries had to be zero because there was no mass flow into or out of the boundaries, and that allowed us to set the stream flow value on the boundary. Whereas when we do sea level, water level, we need to determine the boundary conditions for pressure gradients and pressure at the boundaries. So we end up with a little bit more work to do. So now we have the Neumann boundary conditions. So the pressure gradient at the boundary has to be constant, which doesn't allow us to set the pressure at the boundary. So we have to find a ways to determine interior solution and derive the value of pressure at the boundary as well. Okay, so that's the Neumann boundary condition. So this term goes to zero in the case of this boundary value problem. So like before, as we defined for, by the way, in the previous podcast there was some noise because of the winds. I have a nice breeze coming through my window, but I closed it because it's too strong and can create noise. I listened to the podcast, the sound is okay, but if you're unhappy with it, let me know and maybe I can re-record it. Okay. So the integrated pressure similar to transport is now defined from the bottom to the surface height as PdZ, integrating in the vertical. We take these equations again and do as we did before, ddx and ddy. This time we add instead of subtracting, and we again assume that surface height is variation is much smaller than the average depth of the water column, which is a very good assumption in the real world. So that gives us, again with our original continuity equation, divergence of m, the transport, dmx dx plus dmy dy is 0, which allowed us to define the stream function mx and my, which naturally satisfy the continuity equation. So using the Dirichlet boundary conditions, we have to first derive psi, and then we can use that to solve for the sea surface height, which is related to pressure gradient. So our equation now is grad square p, again a boundary value problem given with f grad square psi, which is derived separately or solved for separately, plus beta del psi del y, plus the forcing in the x and y direction at the surface, and tau xz again, like before, as Stommel did, we can assume a simple wind forcing with meridional wind stress being 0 because it's fairly small in the real world, so it's fairly realistic. Obviously you can do this with more realistic forcings as well, and the zonal wind stress is set to some amplitude with a meridional distribution, so you get trade wind like and westerly like forcing with wind stress curl. So del P del X is F del psi del X plus tau x z equal to 0 at x equal to 0 and x equal to L in our rectangular domain as before. So we are setting the pressure gradient at the x and y boundaries. So del P del Y is equal to F del psi del Y plus del YZ at y equal to 0 and y equal to B. So we don't know the value of P at the boundaries, but we are setting the boundary condition of the gradient being constant so that we still have flow parallel to the walls and not into the wall. So the pressure gradient has to match that condition. So by calculating Pxy based on 645 and considering 646, the boundary conditions, we can determine the elevation of water surface using 644, which is just the integral we defined. So the integrated surface distribution in the water column has to match the surface elevation for this simple situation. In the real world, you have a deep ocean with a vertical structure, so you can do the same thing but only down to the so-called level of no motion, which we will not worry about here. Okay, so the distribution of pressure then Pxy is minus h to eta rho times g times eta minus z dz, as if you remember the hydrostatic equilibrium gives us that pressure at any depth z is just equal to the weight of the water above it. So eta is the surface level, z is the depth, eta minus z is the water column, times rho gz is the mass, so we integrate that in the vertical. That gives us 1/2 of rho gz times h plus eta squared, and since eta is much less than h, we can write this part as Pxy, so this equation we are writing as half rho g h squared times 1 minus eta over h to squared. Nothing changed here, but when we expand this, 1 plus 2 eta over h plus eta squared over h squared. The last term, eta squared over h squared, is too small because eta is much smaller than h. So then this basically becomes 1 plus 2 eta over h, which then becomes approximately equal to 1/2 of rho g h squared because of 1 plus the 2 gets cancelled, so rho g h times eta. So I've dropped the eta squared h squared term here, or basically eta squared term here. So eta xy is approximately then equal to Pxy divided by rho g h minus h divided by 2. Okay, so we have now the solution for sea level in x and y, but we are still left with the problem of, so the numerical solution to this boundary value problem can again be done with the successive over relaxation that we discussed in chapter 5, like we did for the Stommel problem as well when we looked for stream functions. Even though with the given assumption about the wind stress, it can be solved analytically by separation of variables. So to match the boundary condition of the pressure to the pressure gradient, one can use interpolation methods to the interior solution. So you have to kind of solve for both here. You have to solve for interior solution, prescribe the gradient at the boundaries, and then solve for the boundary value of the pressure. So interpolation of the solution function at the boundary using parabolas. So you can go from the right boundary n delta x to the interior, and from the left boundary to the interior like this, by prescribing a parabola y equal to ax squared plus bx plus p0 and similar equation for Pn, of course, and also for the meridional boundaries, similar equation works. So how do we do it? You write P1, so you are at P1 and P2 and looking for P0. So P1 is A delta x squared plus P delta x plus P0, and P2 is A2 delta x squared plus P2 delta x plus P0. So P0 is not known, so we are, and of course P1 and P2 are also not known. We have to solve for those. So we solve together for A from here, P2 minus 2P1 plus P0 over 2 delta x squared, B as minus P2 plus 4P1 minus 3P0 over 2 delta x, and plug it into y equal to ax squared plus bx plus P0. So we are setting dy dx at x0 equal to b, that is by definition what we said, the gradient at the boundary has to be constant. Then P0 can be written as 4P1 minus P2 over 3 minus 2/3 delta x dy dx at x equal to 0. And similarly at the right boundary, Pn equal to 4Pn minus 1 minus Pn minus 2 divided by 3 plus, so similar expression with a different sign because you are at this end, plus 2/3 delta x dy dx at x equal to L. So now we have all the equations we need to solve for interior values for the boundary gradient of pressure at the boundary and pressure at the boundary as well. So slightly complicated, but still the same thing. The surface elevation then solved numerically again with these boundary conditions and successive O relaxation by first deriving stream function with the Dirichlet boundary condition as we did before, which is a well-defined problem, I mean less complicated. Using the Stommel model, panel is for beta real value, beta equal to 0, so the F plane, and when you set F equal to 0 so that there is no rotation and you still have wind forcing in the flat bottom basin, rectangular basin, parameters are set at the decay time scale r equal to 1 hour 6 days, h is 1,000 meters, 1 kilometer deep basin, wind stress amplitude is 0.1 newtons per meter squared. Numerical solution of 6.45 and 6.46 were calculated on a grid with nx equal to 100 and ny equal to 20 using the method of successive or relaxation. So I don't know if I want to go back all the way to 646 is the pressure equation and 645 is this. So these are the boundary conditions and this is the governing equation knowing psi from before. So the solution here with beta equal to 0 for the sea level, again you have western boundary intensification, so you can see the sharp pressure gradient which has to remain constant, and the doming of the water in the gyre is seen here with positive eta, and around that you get negative eta. So there is a wind forcing that is creating western boundary intensification as seen with this sharp pressure gradient, and doming of the water as seen with this positive sea levels, and sea levels then are negative with respect to the mean height at the eastern boundary and northern and southern boundaries, as well as the value goes negative along this boundary as well. So here you get a balance between basically frictional force, Coriolis, and pressure gradient, whereas here you get almost a geostrophic balance when beta is 0, no boundary intensification. Here wind forcing balances the frictional force, and pressure gradient almost balances Coriolis, which is what is geostrophic. But in this case you can see that the dome is not asymmetric, so you have piled up water in the middle with when F is constant on the F plane, so you have dropping off, the flow dropping off from the peak here. So you can imagine that the wind stress curl is piling up water in the middle, and there is gravitational flow downhill, and there is partial geostrophic balance, and wind forcing and friction are balancing each other as well. So sea level is negative with respect to the mean height here and positive here, whereas if there is no rotation, then wind forcing is pushing water this direction. So there is low sea level here piling up against this boundary. Wind stress is this way, so pulling water from here, piling it up here. So this is the solution for sea level distribution for the same set of equations that we looked at before. Okay, I went through a little bit fast maybe, but the idea is to look at how climate modeling works and how numerical methods work and how boundary conditions work and how the boundary value problem work for stream function and for sea level. Okay, so just make sure you read the book and listen to the podcast. Make sure you understand all the important points. Okay.